Today we're going to look at the implementation of BFS, DFS and a few variations of A* in the maze environment. Let's take a look at BFS first. So BFS is an uninformed search algorithm, which means it knows how to traverse and it knows how to find the goal, but it doesn't know what is right or wrong and doesn't care about how efficient it is. First, we're going to import some modules over here. The first one here is PyMaze, and we import the maze, the agent behavior, the color definitions, and the text labels. Then we import timing from Timeit, and a double-ended queue, which is a deck, where elements can be added from each side. BFS is most used to find the shortest path between nodes, and it will find it as it will search level by level, and so once it reaches the goals, it will know the shortest path, and there cannot be a shorter one. BFS uses a queue data structure to maintain this order of exploration and ensures the nodes are visited in the order of discovery. The queue data structure enforces the breadthward movement of the BFS algorithm. So over here, we define BFS and tell it there is no start, so it starts bottom right. Otherwise, we would put the starting point over here. This is where it creates the frontier, the deck, the path dictionary, an explored list, and an empty list for the order of cell exploration. This performs the BFS algorithm, exploring cells in the specified directions and based on the maze structure. The algorithm stops when it reaches the goal cell. It adds the cell to the frontier and it marks it as explored. It adds the child cell and its parent to the BFS path to update the search order list. Then we have a dictionary which traces the path from the goal cell back to the start using the BFS path dictionary. This is where it returns the search order, the path, and the forward path. And then we've got the main function. So this bit here ensures that the following code block is executed only when the script is run, not when it's imported as a module. So we've got mmaze88, which creates a maze of size 88. This bit over here either creates a maze, which is how I did this. This one loads the saved maze. Finally, here we've got the bit that actually executes the BFS algorithm on the maze. We defined our agents here, then we just trace the paths of these agents. Then we just label these, so at the top we're going to be able to see what exactly they're doing. And obviously the timer, which is very handy when we're trying to make some comparisons. Over here we can run the program, and so we're just going to go start. This is where we can think about whether this is truly the best solution. BFS does the job, but it takes an awful lot of time. In this scenario where the maze is pretty small, we get away with it. If this was a video game and we had a small maze, that would be fine. But what will happen in a game where the maze is much bigger? How long does it take to execute BFS then? Well, if this maze, which is 8 times 8 nodes, takes about half a second, then much larger maze, which is 40 times 50, like this one here, actually takes just over 80 seconds. It is quite likely the game would have an even bigger maze along with computational processes, and the player would get bored and do something else instead. So while it finds the optimal path, perhaps the time it took to execute is not a great trade-off, and this is where we think about implementing DFS or A*. So this is the DFS code. It selects the starting node and marks it as visited. A stack is used to keep track of the nodes. It explores depth. It goes as deep as it can on each branch, and it revisits the nodes using the stack and explores alternative paths. It most likely won't find the optimal path and may not visit every node. So if we just press play here, it started at bottom right again because we did not define a start, and is just slightly out of our reach. Now here we can see how it's searching down every branch, and we might be thinking why it's not going to the right as it's so close to the goal, but obviously it has to search each branch. Now the biggest problem I've had with this code is that I was unable to get it to trace the path back. If we close this and we go over here, we can see there's an error, and I can't find the reason for it. I've tried multiple ways to get around this, perhaps building in a different timer or a different way of storing that timer, but PyMaze did not support that. So What I do know, however, is that if we do just comment out the top 2 agents and the top 2 tracking paths, then if we run the program, it will actually trace the path. So that's the way around it. And here we have it tracing the path back to the start. Finally, here we've got the A-star algorithm. A-star assigns a heuristic value to each node in a graph. It calculates the cost to reach the goal from that node. It creates an open set to keep track of nodes to be evaluated and a closed set for nodes that have already been visited. The nodes are selected based on their cost and heuristic value, prioritizing lower cost, some of the costs to reach the node, and how much it costs to reach the current node. Nodes are expanded by checking the neighbors and calculating the cost to reach them. It updates if more efficient path is found. If the goal has been reached during the expansion, then the optimal path is constructed. So it starts bottom right again, and in this case we have the goal over here, and we can see how quickly it found the goal. On the right over here, we've got an execution time label, which at the moment says 4.8. Sometimes it's a little bit different. It just depends on what else my computer is doing, I believe. So again, here we have the problem of it not tracing the path back. There's this error again. Again, I just comment out the agents normally, and I'm able to trace the path back. It's the saved maze, so it ran on all 3 algorithms. And in this scenario, the A-star algorithm ran at 4.6 seconds, and it explored 71 nodes, and the path length is 67, which is the optimal path. So there seems to be an issue with the way trace path function is being used for agents A and B. So I tried to modify the path and use different dictionaries for each agent calling trace path, but that did not work. I tried to use a move method, then I tried to use set position to manually set the agent's position and track that, but that also did not work because it was not supported by the amaze structure. I even tried to draw points to directly draw the paths for agents A and B with a delay, and then use trace path for agent C. But again, that was not supported, so I ran in quite a few problems here. Because in maze 1, the smaller maze, A-star didn't perform as well as I expected it, I created more mazes, but I also tried to implement other algorithms, and this is why I have Manhattan squared, which is A-star squared, and even the Dijkstra's and a couple of other ones like these ones. But perhaps the reason it did not work is that BFS found the solution earlier as it was going from that direction where the goal was. It just happened that DFS was more efficient, but if the goal was on the right, then it would not be as efficient, as evidenced by my other mazes where the goal is closer to the middle of the maze. That was an interesting endeavor where I just try to implement as many algorithms as possible and see how they function. But all in all, the A-star algorithm was the most efficient, it explored the least amount of nodes, and it had the fastest execution time.